So as soon as I assert something that you don't understand or you don't agree with, please shout out.
Don't raise your hand, just shout.
Okay.
All right.
Got it.
You got it.
Yep.
Sounds good.
I would like to make some specific points and talk about some specific ideas. And I'd like to tell you what those are at the beginning of the talk so that you can look out for them and see whether I have made the case or not. The first thing I'd like to talk about is the magnitude of space resources. Secondly, I'd like to talk about the economic rationale for going to space. The role of the government, the role of private enterprise, and I'd also like to address the question of how much investment is really necessary for the breakout into space to occur. I'd like to talk about the other rationales for going to space. So the fundamental ideas that I'd like to talk about are, again, the enormous magnitude of space resources. I would like to talk about why free space colonies are really the best place to site the first colonies off the Earth, and why they will be, for sound economic and physiological reasons, always the best place, better than the Moon, better than Mars, better than anywhere else. The next idea is that we can't count on the government. All of us who thought 30 years ago that the space shuttle was going to open up the space frontier had our hopes dashed. There are fundamental reasons why the government will not open space directly. They can be an enabler. They won't open the frontier. We have to do that. There is a commercial path that allows us to do it on our own with less investment than most people would believe. At least most people raised on the $150 billion cost of the Apollo program and the greater than $150 billion cost of the Space Shuttle program. Put your faith in rockets. We don't need devices made of unobtainium. We don't need devices that need a traffic model of millions of tons of cargo per year to make a profit. Rocket technology, as Elon Musk and Jeff Grayson and others in the industry have recognized, was immature. It was not optimized for economic purposes. You can't to assume, as many people have, that because there's been little progress in the last 50 years of rocketry that we're as good as we can get and we need something better is false. The primary benefit to space settlement and space industrialization initially will be to the people on Earth. And that will come in the form primarily of access to clean energy and new materials that are in short supply on the Earth. Asteroid defense is something that the human race has got to do. Some folks have realized that and have taken steps to instantiate a program to do that. But I'd like you to understand that if you can mine asteroids, you can divert any asteroid you want. The technology allows you to mine asteroids, allows you to move them, as long as you see them with enough time to place men and equipment on that asteroid to move it. So please shout out any questions as soon as they occur to you, and let's proceed. So, mine the sky, defend the Earth, settle the universe. Click.
Easy enough.
Konstantin Tsiolkovsky, working in the previous century, was the first man to show how you might make space settlements. And he sought an economic rationale for those space settlements. The first rationale was that you would build mansion greenhouses away from the Earth's shadow. And living in cold, dark Russia with a 4-month growing season or 4.5-month growing season, he greatly appreciated the value of full-time solar energy. Tsiolkovsky also, surprisingly, developed the rocket equation, something that Newton could have derived but never did. He wrote a classic book called The Dreams of Earth and Sky, and his plan to settle the universe was predicated on the delivery of economic goods to the Earth from space. He didn't know about power satellites, but he thought maybe we could get some gold or diamonds from the asteroids and bring those back and finance space settlement in that way. There was no thought at the time of a vast government program that would just do it for the good of everyone. Click. The Space Studies Institute was founded in 1977 with the purpose of completing the missing technical pieces to allow human settlement of space. And at the time, those were things like the location of asteroidal resources. So we undertook in 1979 searches for near-Earth asteroids, thinking those would be ideal places to go to get materials. And that was before we realized what killed the dinosaurs and that the near-Earth asteroids were a much greater population and a much greater threat than we had conceived.
Can you provide a definition for free space?
Free space means away from planets.
But still access to a star, correct?
But still access to a star. We're looking to stay close enough to optimize radiator mass versus energy collection mass.
So Lagrange points in an orbit would be an example of one of those places?
Pardon?
Some of the Lagrange points would be an example of a free space?
We love Lagrange points for all kinds of reasons.
Yes, we understand.
Speaking of Lagrange points, I just had a note from Bob Farquhar, who has used Lagrange points in just yesterday, who's used Lagrange points to send the first Comet Rendezvous mission off, repurposed. And if we want to talk about using the moon and getting to Mars via the moon, the L2 Lagrange point is something we really have to think about.
You might want to define the Lagrange points for the audience.
Lagrange points, also known as Euler-Lagrange points, are points in a two-body problem. So let's say you have the Earth and the Sun, two bodies. You ignore the rest of the bodies in the solar system. As those, if you make a line that connects them, that line always stays pretty much the same. Then there are 5 points in that system that if you put a body there, it should stay pretty close there without having to move it, accelerate it very much. So in the two-body problem, there are points here and here, points here and here, and a point on the other side. So the L2 point in the Earth-Moon system would be, here's the Earth, here's the Moon, L2 is right here, backside of the Moon.
These are places where the gravity of the two bodies cancels each other out and leaves a nice little spot for something to sit without being pulled one way or the other.
It's kind of like a well. Something can sit in the well and it won't tend to pop out of the well, so it's stable.
Gravitational stability.
Yeah.
Or somewhere like a saddle where you're okay in some ways, but then you can fall out one way or the other easily.
Yeah, but you can spin around on the inside of the bowl. And that's a key idea, that you can spin on the inside of that bowl so you can orbit the Lagrange point. It's kind of counterintuitive, but and it took...
One of our near-Earth satellites is doing that, as I recall.
Yes.
Yep.
It's a nice place to put things if you want them to stay in a stable spot. So the advantages of being in free space are that you have access to energy full time. That's a huge advantage because it means your agriculture can be very efficient, 6 or 8 times more efficient than agriculture in North America because you get 24-hour sunlight that you can optimize. It gives you, if you're in free space, you have access to high-quality vacuum, which is important for many, many industrial purposes.
Are you in zero gravity? Or do you spin or do
Well, the idea is that you would really spin. When you spin the habitat, you can give yourself full Earth normal gravity. So you don't have to worry about, well, if I live on the moon, will I demineralize so much that I can never return to Earth? Or if I live on Mars.
Provide context, demineralize.
Demineralize means your bones are a dynamic system. As soon as you put a load on the bone, it senses it, and if it's getting too much load, it builds itself up. As soon as you deload, as soon as you take the load away from the bone, it starts to demineralize and weaken. So if you want to weaken your bones, just lie around in bed and you'll weaken your bones. It's not really known because no one's done an experiment to determine whether or not people can survive and reproduce in moon gravity or Mars gravity. That's an experiment that should be done, hasn't been done yet. You could do it with an orbital facility with variable rotational artificial gravity. But the idea of free space colonies is that you would have sufficient spin to give whatever gravity you would desire.
Lee.
But on the spin axis, you get zero gravity.
Lee, I have a question.
Sure.
How complete would you say is our understanding of the effects of microgravity on the human physiological health? I mean, we've had people at the ISS for a while now in Mir, but we haven't been able to do like reduced G experiments, right? You know.
No, we have the 0 G point, we have a 1 G point, and we have some points at 2, 3, 4 Gs. Those are on chickens and rats. But chickens and rats are pretty similar to people in certain ways.
Chicken shorter than a 1G chicken?
Oh yeah, 4G.
Depends on your frame of reference, Clive.
It's a great mambo chicken. They put sumo wrestlers to shame. The great mambo chicken.
Do we care about that, though, if we're in space indefinitely? I mean, the only reason we care about bone loss is to come back to Earth and be able to survive there.
Yeah, I think that's right. We don't know really whether people can effectively reproduce in reduced gravity. It's not known.
You adapt to it, right? So the people who
You would think it would probably work. Yeah.
You're right. That's how
Or we return
Yeah, you don't know when something is going to come along that's so devastating no one can mutate.
we have to return to
If
Earth
you
to
end up
spawn.
with too much bone loss, you end up losing the spongy part, bone marrow.
Yeah.
It supports the marrow, and you can have problems with blood
Yeah.
cell generation. So
Yeah,
it's properly supported.
in any complex engineered system, it's always a good idea to test things before you put them into operation.
That's why don't we test the reproductive stuff?
There were some experiments done on the shuttle in that regard. We know that because of accelerometers placed around that.
I thought you were going to talk about rats and chickens getting together.
My understanding is that the Russians had tried to get rats to reproduce in space, and that there were two problems. That they were having some difficulty encouraging the rats to actually mate, and then once that happened, I heard that there was something going wrong with the implantation of the fertilized egg in the uterine wall. Is that correct? Or
Molly, I don't know the answer to that question, but it would not surprise me that there was, because we know that eggs have a gradient that's a density gradient, and you don't have a density gradient in zero gravity. So you depend on the polarity of the polarity of the fertilized ovum is determined by gravity, because the denser components sink to one side, whichever side happens to be down after implantation, and that allows differentiation to go on. Whether that will work in a sixth gravity or in 0.38 gravity, like on Mars, I don't know the answer to, and that's why you have to do the experiment.
But to get back on topic, this is why you're a fan of building large colonies that have their own induced gravity.
Yes, that means you definitely don't have, if you're in one gravity, we've evolved in one gravity, we've evolved over tens of millions of years in one gravity, and we know it works.
I do have one more question about living in free space. It's one I asked when I was in high school to scientists back at the old Museum of Science and Industry, and I'll ask it again now. We live in this wonderful shield of Van Allen radiation belts that helps keep us from being bombarded by both the solar wind and cosmic particles. How do we deal with that in the free space situation we're talking about?
And don't forget the atmosphere. That's really good too.
I'll get there next, but one physical effect at a time. But to me, that's always been the long pole in the tent in terms of keeping people in space for prolonged periods.
Yes, it is. And the answer is you have to live behind a thick shield, meters thick. But same thing is true on the moon and on Mars. You know, these dome cities are fancies. They're fanciful. They cannot work for that reason.
Okay, that's what I was expecting you to say, but I just wanted to, maybe you knew something that I didn't.
No, we have designs for space settlements that truly the shields are meters thick.
Yeah, so you got meters thick of 4 pi shielding. Okay.
Yeah. Okay. Click. I wish that I'd had somebody to help me trying to communicate the magnitude of resources that are available in space. It's really hard to do because they're so huge.
Just like
3 times 10 to the 14th terawatts, you can say 3 times 10 to the 14th terawatts, and what does that mean? Well, it means in a few minutes, in the time during the time I'm going to give this talk, the sun will have put out more energy than the human race at its present rate of using energy will use up until the sun dies.
But that's spread over a massive area. Right, I mean, so per square foot of what we got on the planet, I mean, take away the atmosphere, do we get 500 million times more? No.
No.
Okay.
Total solar output.
Total solar output.
Total solar output. Okay.
Yeah. So you if you want to capture more of that solar output, go out into deep space and put habitat after habitat after habitat, and then your surface area that you're collecting becomes greater and greater. And if you do that for a long enough period of time, you'll create a Dyson sphere.
Mm-hmm.
So the advantage there is really the space available, less the energy density.
Yes. Yes.
The energy density isn't bad. You know, the size of that cube behind you there, one face of that would get about 1.5 kilowatts of power.
Oh yeah, more than that, Doug. These are both well over a meter.
It's about a square meter.
Yeah.
Is there a sweet spot between here, the Earth, and the orbit of, let's say, Mercury, where you could put these habitats that is enough to gain an enormous advantage in power generation output and not close enough to melt immediately?
Oh yeah, you can fix things so you don't melt immediately all the way down inside Mercury's orbit. But you'll just get hot, and you have the problem of radiating that heat away. In terms of where you want to site a habitat, it's probably that you want to site it someplace where you've got the materials to build it from, or you can get the materials easily to build it from.
Without having to pry it out of the gravity well.
Without having to get it from someplace that is hard to get from. So you could put these in Mars orbit, and you might use Deimos and Phobos as a source of materials. You could put them in the Earth Lagrange points, or orbiting the Earth-Moon Lagrange points, and use material largely derived from the Moon. But as I mentioned earlier, there's a dynamic trade-off between the amount of energy gathering equipment, mirrors and solar cells or heat engines, and the amount of radiation equipment you need to get rid of the heat. So there's a sweet spot someplace on that metric, but I think it's going to be driven more by where the resources are than by that particular thing. I'd like to point out that the energy flux in geostationary orbit, if you consider a band 15 kilometers wide, is 200 times greater than current energy consumption. And that just tapping a small fraction of that energy will allow you to power the Earth's industries at a U.S. standard of living with a population of 10 billion people in 2050 indefinitely. So this is an argument for satellite solar power as a solution, a long-term solution to the need for clean, reliable electrical power.
What are the ways that power gets down to the surface? I've always missed that part.
Well, you have to change it to some different frequency of electromagnetic energy. The most efficient way to do that we understand today is using radio frequency waves. The disadvantage is that both the transmitter and receiver have to be pretty large. You can also use a tight laser frequency and use solar cells as collectors or heat engines as collectors. And that can be pretty efficient if you tune the laser frequency to the optimum frequency of the solar cell collectors. So the answer is, yeah, the answer is frequencies somewhere close to the visible spectrum and very high frequencies in the gigawatt, or in the gigahertz frequency range.
Wouldn't a big space laser get weaponized pretty quick?
If you don't consider the numeric magnitude of the problem, you would think that it might be, but the answer is it will not really be possible to do that.
Even with a laser, it's hard to get a spot size at the surface of the Earth that gets high enough power to cook an aircraft, to cause thermal damage to something.
Yeah, it's very
difficult to dazzle someone with a visible light laser, but you're not going to be able to cook anything. And so it's essentially useless as a weapon.
And it's easy, and it's a sitting duck for a laser on the ground or a fast-moving rock.
If you know what you're shot at by a laser, you can have a mirror shield which can survive long enough for you to do an impact destruction of the laser. So if somebody with a laser power system in orbit threatens to use it as a weapon against facilities on the Earth or elsewhere, there's the simple, that's an act of war. And anyone faced with an act of war like that is entirely justified in shooting down the laser source. So that's the strongest deterrent against anybody doing something stupid with a laser.
Did not the Russians shoot the space shuttle with a laser a couple times?
That was harassment. Yeah.
Think of it as a big boy version of the laser pointer game, right?
I'd also like to point out that any technology could potentially be weaponized, and that's not an adequate excuse to not develop that technology.
Yeah, but you would expect for a product to have fail-safes and other things built into it. So from a technical perspective, you can make it so that it has certain safeguards against accidental
That's
pointing.
correct. And in a properly designed power system, it is very difficult to weaponize that, and further to weaponize it without somebody noticing, because it's in full view of anybody with a good telescope.
Yeah, if your transmission optics for your laser power system are larger than a certain size, people are going to notice that and say, hey, what are you doing there? It's that simple. It's that you can't hide something in space. It's out there in sunlight, and it's brightly illuminated against a black sky. You can't keep it hidden from all points of view. You can mask it from one direction, but other observers elsewhere will still be able to see it.
Nonetheless, these arguments will be raised. Click. We already started to talk a little bit about the criticality of space transportation, because if it doesn't fall by a factor of about 50 at least from where it is now, none of this can can happen because we can't afford to do it. And I want you to all put your faith in rockets because combustion rockets are good enough to do it. There's new technology in rockets. You've seen SpaceX Falcon 9. Probably as good an EELV as anybody can make. They're embarking on a program to make the thing reusable. Good. I hope they succeed because we need something that can launch big pieces. The critical technology is rocket engines that have long life because a large fraction of the cost of a launch vehicle is the engine. Mm-hmm. Typically, rocket engines, for example, the Saturn V main engine was good for 25 to maybe 50 on-off cycles, maybe 50 thermal cycles. There's a rejiggered Russian engine called the AJ-26. They think it's good for maybe 100 on-off cycles. But if you really want to make things inexpensive, you really want jet engine reusability and operability. So you want hundreds or thousands of flights per engine before they have to be scrapped. Until this last decade, we didn't have that. But now we have engines that have run more than 500 flights, at least at export. And that engine design is scalable. We're building at X-Core, folks are building a 25,000-pound thrust class engine with the same kind of technology. So that engine should be good for landing on the moon and taking off again, and landing and taking off, and refueling on the moon and landing and taking off, and shuttling things from low Earth orbit to higher orbit, or from Earth-Moon L2 to Mars, refueling on the moon. So the engine technology is key, and that's going to be well in hand very soon. Of course, you need markets. The encouraging thing is that there is a market at the lower disruptive end of the scale. Both Virgin Galactic and X-Core have sold hundreds or so of tickets. I think Virgin's probably sold close to 500. We're somewhere over the 100 mark in ticket sales for various purposes of suborbital flight. And the systems on the Link spacecraft are systems that will go into the upper stage of the orbital system. And there are systems that will stay in the lower stage of the orbital system. So let's quick. New markets, personal spaceflight, space solar power, affordable science, low-cost satellites. Let's talk about that a little bit because we haven't talked about that. Everybody knows, I think, in this audience that satellites, communication satellites, typically cost $250 million, $350 million, $1.5 billion. And the reason for that is pretty straightforward. They have to withstand the rigors of the launch. They have to withstand launch vibration and acoustic loads. They have to self-deploy. There's nobody there to unfurl their solar sails or their antennas. They have to use the highest quality components that are exhaustively tested because they can't be repaired in situ. They have to last for 15 years without anybody putting a wrench on them. And the reason for that is that launch costs were very expensive, so it made sense to make satellites like that.
You actually pay the most for the testing. I mean, I do specialty engineering for military comsats, and the big driver for that is the testing, because you have to be absolutely certain within a certain statistical chance that it's really going to work. And
let me ask you a question.
Sure.
If you could design a military satellite to do its intended purpose, and you had whatever budget you want, but you want to minimize the amount you spend on that satellite, but you can assemble it in orbit, you can use whatever components you want, You don't care how much it weighs.
Okay.
How would you design it? You can assemble it in orbit from components you take up, or sub-assemblies, however big you want to make it. You can make the satellite as big as you want. It doesn't matter how much mass it has. How would that change the design of those satellites?
I would aim for a modular system that was much easier to test. And I would try to design the thing so that you could prove out technologies, launch pieces of it, do it piecemeal rather than doing it all beforehand.
Well, I forgot to tell you,
have to
you can
distribute
send
it.
a repairman.
Well, if it's a line repairable unit system, then I don't need to test it so much. I can drastically reduce
It
it.
will be smaller than it is now.
Yeah.
You also don't need to
You'll
spend
need
a
three
lot of
full
time and
toners,
effort
yeah.
making sure that it fits under a fairing. You can build it to size immediately. You don't have to, these incredibly large, delicate systems, you spend the majority of your time and energy trying to get them to survive launch. And once they're up there, you don't need the majority of the strength that they have.
Well, actually, you always have to double it or M for N because you've got redundancy. If you could greatly reduce the redundancy, it would drastically reduce how much you have to overbuild it just to survive the component launches that you were alluding to.
Yeah.
Yeah, so your whole design would be geared more toward maintenance and repair on orbit rather than doing all the redundancy and failover pre-launch.
Another thing that you can do, and it's something they talk about nearly enough, you could put the sensitive parts inside a pressurized enclosure.
Yes.
And now you're dealing with the same hardware that goes into airplanes, which is,
Yes.
by space standards, dirt cheap, reliable, well tested. It will not work in a vacuum, so we can't use it for satellites now. It won't work in that environment.
Wait a second.
Right,
The
we hold our
first
nose.
satellite used that.
Really?
Yeah.
It didn't
Yeah,
last
that's
very
okay.
long.
Yeah.
Well, that's because the Russian
Lost pressure, yeah.
We hold our
didn't lose
nose.
pressure. Didn't lose pressure. Just that the battery wore down. They just used a standard old crappy Russian battery. But a friend of mine sealed that up.
Yeah, we hold our
It
nose.
was, but it was Earth normal pressure inside Sputnik 1.
Yeah, we hold our nose. We call that avionics grade in the satellite world. It doesn't cut it for us. Yeah, that's equivalent to saying junk.
Yeah, thanks, Don. I like that. Good. Avionics grade. Okay, so there's a market for personal spaceflight. Really rich people can afford to go to orbit. Space solar power, we talked about a little bit. We can talk about that more later. But I will point out that if the Japanese had an ability to assemble a modular satellite in orbit 10 years ago, they had a plan to build a demonstration power satellite. They couldn't figure out how to deploy it. They knew they had to have people to assemble it, and they didn't have that, so they couldn't do it.
Gosh, if only there were some companies trying to put more people into space.
Damn.
Well, I know of one company represented by folks here that could do it
Well, we
this
did
year.
that with ISS. I mean, ISS was modular. It was built by people up there. So, but a lot of people consider that to be overpriced, in a way, failing to meet its expectations.
Well, NASA refused to use avionics grade materials, and they, time and again, they required design of new components rather than taking stock off-the-shelf stuff. Even the equipment racks aren't 19-inch standard equipment racks. They had to come up with their own new non-standard standard.
And even the stuff that they built for it, they didn't reuse. It's modular, but each module is individually designed.
Really?
Pretty close.
Yep.
Yeah.
Need those jobs now.
That's the problem with standards. It's that second S.
Yes, good. All right, we talked a little bit about low-cost satellites. There is one point I'd like to make, and that is that economic development of all sorts brings fortuitous benefits to science. For example, we really first understood the unfolding of the history of life on Earth because the British dug canals. And what might you say do canals have to do with understanding life on Earth? And the answer is, when you dig through all of that sedimentary rock, you find all sorts of interesting fossils they weren't known about. You can also talk about the voyages of Captain Cook. Those were undertaken with the converted Whitby Collier, ship that carried coal in England. and just had a huge scientific output with standard off-the-shelf technology of the 18th century. Click. Economic drivers, we talked about these a little bit. There's a old power satellite design you can see, and a receiving antenna on the surface of the Earth. You get a kind of an idea. That's a big thing. It has to be big to be efficient, catch the energy. We talked about platinum group metals, why they're important. Assembly in orbit, why it's looks like a winner. Propellant from the moon. We now know, thanks to results from the LCROSS mission, that there's a fairly lot of water on some spots on the moon. And so it should be fairly straightforward to extract that water. It's in abundance of on the order of 5% in some spots, to make liquid oxygen and liquid hydrogen to use as rocket fuel. When you do that, you guys at SpaceX can tell Elon this, because I don't think he knows it. You can use a propellant depot at Earth-Moon L2, and that gives you a direct gateway to Mars. Click. Here's a partial answer to your question, Clive, with the steps between from small ships like the Lynx to orbital systems to how are you going to mine asteroids. Well, you need someplace for the miners to live, and those might grow out of space habitats such as this Bigelow aerospace module. There's a study done by Boeing under NASA Aegis about 30 years ago that showed pretty conclusively that for any manned space habitat of any description, whether it was in low Earth orbit or on the moon or wherever it was, would benefit economically from a closed environment life support system if it were going to be continuously manned for more than 5 years. So obviously that would benefit the space station, except it was not designed with that in mind. The technology of closed life support systems is not fully developed yet. Nobody's built a really good system. At SSI, we think we know how that should be approached, but not exactly how to do it. And we think there will be a market for that kind of a system, whether it's Bigelow Habitats or somebody else's. And that is a key technology that will be economically driven.
Well, if it's only 80% closed, then it takes 7 years for it to be.
I think the arithmetic is not exactly
but
quite
it's
like
kind of
that.
like that, you know.
Yes, something like that.
There's a curve.
You get a huge benefit just from getting the water out, but depending on how you get the water out, you can get another huge benefit really easily. Mm-hmm. It's the last few percent that cause you some headache. So, and this is a artist's conception of the interior of a very large space habitat. So you can see things could be really nice and Earth-like in the interior of such a structure. Quick. Assemble in space, we talked about that, the reasons for that. I've got another reason that I didn't know about. Great. Next. Satellite solar power. Here's a new design. Let's say a few things about satellite solar power, because I know Elon does not like it. He doesn't believe in it. And my theory about his disbelief is that he didn't think he could get costs down low enough to make it worthwhile. John Mankins, who was NASA's last previous chief technologist, is a senior advisor of the Space Studies Institute. And he and Professor Nobuyuki Kai made a visit to us in Mojave a few months ago. And they told us that if we can get the cost per pound to low Earth orbit to $200 or less, then they can build a power satellite that'll supply energy at a competitive cost. Not competitive with ground-based solar, cheaper, competitive with standard, really economical ways of generating power, like coal-fired power stations or nuclear power stations. So $200 a pound is where you want to be. So if you get that grasshopper hopping, with some luck, we'll be there. Before we leave this slide, I did want to say one thing, and that is that although it seems likely to me that the first demonstration power satellites and probably the first commercial power satellites will be built totally from Earth-launched materials. Because of the great advantage of using extraterrestrial materials in terms of cost, at least when the extraterrestrial economy has grown to a certain point, it might be the best to source materials not from Earth, but from the asteroid belt or from the moon. We did a study about 25 years ago at Space Studies that showed that you could build, under pretty standard constraints, at least 90% of a power satellite solely from relatively crude materials that you get from the moon, from the surface of the moon. And we thought that we could engineer a system to get that material there that would make power satellites much cheaper than you could get them sourcing the components from Earth.
Lee, did that actually include the manufacturing complexity required, or was that just material?
That was the manufacturing complexity, because we anticipated to use the space environment to manufacture things. But it meant that we used relatively simple but heavy radiators, so no real fancy stuff, just simple ass stuff. Yeah, yeah. The power satellites, under those assumptions, turned out to weigh many times more than Earth-launched power satellites. So they were sort of
down your manufacturing a bit, but you could do it up there. So
yeah. Yeah, and we developed some materials, some sintered regolith and lunar glass composites that were perfectly good enough to make structures from.
Where do you want to ideally place a solar-powered satellite? Geosynchronous orbit, or?
Probably in geostationary orbit. Stays over the same spot at one time. There are other orbits that you could conceivably use, like Molniya orbits, that are highly elliptical orbits that have the same property of staying apparently over the same point on the Earth's surface. So as the Earth turns, the Molniya stays over the same.
If it's geostationary, do you have to incline it so it's out of the shadow of the Earth?
That's an excellent question. You get hit by the shadow of the Earth at the equinoxes, that band that's in the Earth's shadow, and they get shadowed for about 45 minutes. So you have to devise your terrestrial electrical infrastructure to account for those shadowings at the time of the equinoxes. So most of the power satellites will be in full sunlight, except for those in that narrow band of Earth's shadow.
Because you're power beaming, you can have several satellites supplying power to a given station on Earth, so that if one of those satellites drop out, the other ones can continue to supply power to you. So you don't have to get a blackout on Earth when you get a satellite in eclipse.
Would that be the perfect time to do the bank heist?
There you have it.
I will suggest that you might have to incline the satellite so that it only occasionally jams the communication satellite at the same latitude.
I think all ComSats should be assembled in orbit. They should be huge structures, and they should be all in low Earth orbit so we can get to them real easy to fix them. Get them out of geostationary orbit.
That will take a while, though. We're going to have to share and play nice.
We're fighting a long history, but yes.
Modulate the power beam, you're done.
Yeah. So the power beam is the ComSat. Yeah.
You can probably mine the ComSats that are inactive up there now, all the solar panels they have, and tie them all together.
It's actually, DARPA's looking at doing that right now. They've got a solicitation for microsurgical robotic tool manipulation. They want to go into geo and harvest old sats for that exact purpose.
Sure, that's exactly what they want to do. There's no possible way that'd be totally, like, covered storage or something.
That can't be. That's surgical tools. They can't be weaponized.
So I have a question for you. Has the Space Studies Institute looked at on-orbit manufacturing, like fabrication and so forth?
Yes.
Do you have that available for publication and perusal?
We have a whole series of conference volumes. The most recent one will be coming out in the next, I don't know, a few weeks.
Your conference is the Space Manufacturing Conference, right?
Yes, that's the Space Studies Institute is the Space Manufacturing Conference. You need to come up to Mojave and look at the library. You're welcome. Give me a call.
He's got a really cool corner office.
He's got the coolest office in Mojave.
The coolest office in the coolest spaceport in the world.
It's on the 5th level of the airport tower with a view over the field.
That's nice.
All right, so we talked a little bit about satellite solar power. Oh, also, don't forget that heat engines are good in space. Heat engines are good in space. They weren't used on the space station for funny reasons, but they work fine. And they're easier to construct than silicon solar cells.
They deal better with the eclipses too, because you can throw some mass at the problem and give it enough thermal mass so that it can coast through that 45.
Doug, you're too damn smart.
So by heat engines, you mean like Stirling cycle with
Stirling cycle engines or Brayton cycle engines. I like Brayton cycle engines for a bunch of reasons. Okay, quick. This brings me to my rant, my aerospace rant. If you want to settle space, you have to make it economical. When you discuss things, you have to talk about dollars and cents. You can't talk about mass fraction or ISP or chamber pressure. What else do I want to go on? Or mass fraction or satellite total mass as a figure of merit. You have to talk about what it costs to deliver a service. We all understand that.
Take all of those metrics and make them per dollar.
Take all of those metrics and make them per dollar. Exactly, you got it. That's my aerospace rant, because there's a whole society of aerospace parametricians that do this magic and they trade one thing against another. But the thing they really should be trading against is just dollars. It's just that simple. We talked about advantages of heat engines to make power satellites. There are advantages. And we talked about Earth launch components. Let's go to the next slide. Asteroid mining, we talked about that extensively. Next. Asteroid impact. The one thing we must do is defend the Earth from asteroid impact. If there's anybody who doesn't believe that we can do that or wants to know how it might best be done, ask me.
How do we do it?
Probably the best method is one that I almost but didn't invent. It's called the gravity tractor. And following Newton, two bodies in space mutually attract one another. So if you have one body is a spaceship and it gets close enough to the next body, there will be a mutual attraction. Except the spacecraft can then move away. As it does so, it tugs that body. That's a gravity tractor.
It takes years to do a small maneuver.
Well, it depends on the mass of the body, and we can talk about that because that's where the mining comes in. You don't want to launch a 1,000-ton spacecraft from the surface of the Earth. But guess what? When you get to the asteroid, you can assemble a 1,000-ton spacecraft from loose rubble. Did you think of that?
Yeah,
See, I taught you something.
I was looking for that too.
So now you have 1,000 tons, not just that little pissy ass 50 kilograms satellite that some of the folks associated with Rusty are talking about. Now you can really move things if you have propellant to use or if you have a big solar sail. Asteroids all spin. And if you think about it, and you want to attach an engine to the asteroid and make it go in some direction, it's spinning. So you can't do it. Or you can only thrust a certain time during that, in the course of the spin. You can just thrust when it's at a certain angle. Because if you thrust continuously, you'll be like a pinwheel. You won't go anywhere. So it's a really critical idea to despin, or to avoid having to despin the asteroid. That's a hugely complex and expensive job to do. With the gravity tractor, you don't have to do it. That's why it's so smart.
Implicit in what you're saying for people who may not be physicists is that if you detect the orbit early, and so you can get to that asteroid far enough in time, it just takes a small change in its momentum to make it completely miss the Earth.
Very small, on the order of a centimeter per second.
If you have 10 years to move it the diameter of the Earth,
right,
that tells you how much velocity change you have to put on it. And that's all that you have to move it at most.
Yeah, that's a first. We'll fight about that one because it's not exactly right. You know,
that's the first approximation.
Yeah, that's a good way to think about it.
So your suggestion to use a big mass that's already in orbit to do this is a chicken or the egg sort of thing, right? Because it's spinning too. How are you gonna get that first one?
Oh no, you land on the asteroid and you
grab a small one.
Okay.
Yeah, you take your crew to the asteroid, you load it up with rocks and take off again. So you're just adding ballast.
Despinning a billion-ton asteroid is tough. Despinning a 1,000-ton asteroid is a pain in the neck, but doable.
And
you don't want to despin anything.
64-people session, what we have to do right now.
All right, let's picture it.
Killjoys.